don't know what you just did.
I also don't know what I just did. So.
Are you ready, Paulette?
Yeah, I guess so.
All right, everyone. Welcome to Wonks. Oh my God, it's Paulette presenting for the first time, I think. Everyone, round of applause. Yeah, good.
You guys are very excited about something that I have no influence on. This is somebody else's project. It's over at CMU. Jonathan Aldrich, Joshua Sunshine, Katherine Ye. They're working on that. So, yeah, that's how I actually found out about it, is because I'm applying for an RU at CMU, and this is one of the projects. And so I thought it sounded cool because it's like PL and math, which I like. So, yeah. All right, so as we all know, visualizing high-level concepts is super convenient. We use it for teaching all the time. For me personally, whenever I'm teaching, I feel like super stressed whenever I don't have like a piece of paper or like a whiteboard or something. One time I was walking with Tori, and she was like waving her hands frantically, talking about like arrows pointing like in and out, and she was like, "This would be so much easier with a whiteboard," right? So, you know, if you wanted to visualize something as simple as the diagram I have here, you may want to use something like ticks, and then it ends up being something like this. Thankfully, I did not have to write this. I stole it from their slides, so that worked out for me. Didn't have to. Yeah, right. That's what I heard. That is pretty nice. So thankfully, I didn't have to write this. But yeah. So Penrose, how this works is that it has its two details, right? Substance and style. So they kind of compared it to HTML and CSS, where substance kind of is like the intuitive way we might like to draw a diagram like that, you know, talk about sets and subsets and intersection. And then style kind of specifies how the objects in substance interact with each other and how they should be in the diagram. So like you can see the intersect, you know, they should be overlapping, something like that. So you might be wondering, okay, this is cool, how does it actually work? I mean, we didn't really specify, you know, where should these diagrams appear, about like labels and stuff, because I mean, in the previous one, we have like really specific kind of magic-y numbers, you know, but it's where all the labels go. So the way that Penrose does this is that the user can specify constraints in the style. So for intersection, you might want to say something like this, because I mean, it's kind of dumb to put the label inside of the intersection, labels of the two things, because you have no idea. So you put these constraints, right? And then what Penrose does is it compiles all of these constraints that you set out in style into an objective function, which basically just takes a diagram and tells you how bad it is. And then at runtime, this objective is minimized. So I can show it working in action. This is really cool. You can kind of see how it's like shrinking together to make a better diagram. And there's even like direct manipulation that they do too, which is pretty cool. Yeah, so this is really awesome. I'll just let it play a little bit longer too, so you can see. So yeah. Here's some other examples. So not just that stuff, right? They even have capabilities to make, you know, tree-like diagrams, which are super convenient for us, right? And also stuff with even functions. So yeah, this is all that I have on this because I could only find like a 2-page paper on it. So this is all the information, but thank you, and hopefully I get to work on this over the summer.
Any questions for Paulette?
Yes.
If you get to work on it, what do you want to add to it?
Huh?
If you get to work on it, what do you want to add to it?
Oh God, I don't know. I guess it's like still really, I mean, wonky because like I looked at the paper and then I looked at their GitHub and it's like changed a lot since then. So they're obviously still trying to work out kinks and stuff. But I mean, I would probably want to add like more capabilities for more diagrams because right now the only diagrams they seem to be making are like subset relationships and breed functions.
So I have a cloning issue which I fix with
Any other questions that I can hopefully answer from the 2-page paper?
There you go. You ready to play? Okay, cool.
Okay. I guess that's it.
Any other
Makes
questions? All right, thanks, Paulette. Oh, Aaron, go ahead.
What output formats does it use? Sorry, I missed that.
I'm not sure actually. It didn't specify. I think it's like but yeah, I mean the way that you have to set it up is that you have to set it up in like say the UI that the GIF showed, like you have to have something like that. And to be able to work with that. And so you have to do stuff with like local posts, I don't know.
Okay. It
Stuff I don't
doesn't
know how to
spit
do.
out like LaTeX or technical.
All right, thanks, Paulette. All right, next talk, Matthew.
So, you see the title, Automating Construction of Learning Networks. So this is, I'm going to try to fly through this. I made too many slides and I have too much to talk about, but I'm just going to go fast and hopefully there's time left over. The other thing, this is a couple of papers, so that I basically took, I'm in the probability and EL and learning reading group and the type theory reading group, and so I took a paper from each and saw that they related highly to each other, and so I smashed them together, and that's this talk. So we'll talk about learning, writing that down as a category, how we compile a learning network, and yeah. All right, so for learning, you frequently write out a computation graph, so if we want to think of some function E in terms of A and B, we can write it down piece by piece into this computation graph where the leaf nodes are either variables or parameters, and the interior nodes are each a computation. So we can do some computation graph. And then learning things on this graph is we specify things that are parameters that we will want to learn or optimize or some such. And then we'll have some list of examples. For example, BE pairs, if we consider A to be a parameter. And then if we could do regression on something like that to get an optimal A, of course. But frequently, these networks get huge, and so doing something like least squared is computationally horrific. And so you instead have some sort of update function, which grabs your set of parameters and just steps it to a improved set of parameters. And you repeat this over and over again.
How should I read that expression on the top of the slide? Is that lambda b dot body or?
Yeah. That's just, take a B and multiply, add A to it, multiply things.
And what is
Hmm?
oh, yeah, is that like the overall
is-
expression that graph produces?
Yeah, so this graph takes,
Oh, okay. So,
I mean, I've sort of, it's a little wonky because I have this difference between parameters and variables.
okay. Okay, but that,
But if we're thinking of this as something that takes in B and outputs something, that's the BE pair.
okay, and you're just fixing A there.
A is just some parameter that's unknown. It's the thing we'll be finding out. Yeah. Yep.
All parameters are free variables?
You could write them that way. Yeah, there are different ways. You can specify a parameter set. There are different ways of doing it, but the basic idea is it's some unfixed thing that we're going to learn about by optimizing over everything else. Yeah. So I have no idea how visible this is from all the way out there, but the idea is a bit of motivation. When you do things like this in TensorFlow, it's a object-oriented style where you have a TensorFlow object and you declare variables in it, and then for each node of the graph, you put a line in your code for each single node in the graph. And this seems kind of, like busy work. This seems a little tedious.
And it's not free.
Hmm?
TensorFlow is a paid service.
Could be.
I tried to use it.
Beyond my knowledge.
Yeah.
Okay. Yeah. So instead, wouldn't it be nice to write some parameterized function down and maybe say these are the parameters, and then just have it build us a network and all that. So the general strategy for this, which I should have had a slide here for, is to have an abstraction for these learner networks, and then be able to translate from Lambda terms. Again, I guess I mentioned it briefly. We're sort of thinking about overloading Lambda, right? We want to translate some Lambda expression, some just function that we've written down into a learner network. And so we need an abstraction to sort of represent this. Let's just choose categories. And then we'll think about maybe why that's a good idea. So we can define a category called learn that has objects and morphisms, points and arrows between them. The objects are just sets. The arrows consist of this parameterized function that we care about, which we'll call I, which takes parameters and is a function from A to B with those parameters. And then, so our learner is pi and u, this update function where we take our parameters, examples, A and B pairs that are examples, and we get a new set of improved parameters, as described before. Okay. This is a product we have. We can get into it. It's a monoidal category, which is Cartesian. The Cartesian products are just products. It's sort of the obvious thing, where we have sets as our objects, and so the objects are just Cartesian, or the products are just Cartesian products of those sets. And then all of these, what's called the monoidal product. In other words, we want to have sort of a morphism come up with a morphism based on these products. It takes products to products. And that follows pretty naturally based on right, you just sort of do them component-wise on the products. If that makes sense. Okay. So, the hard part, the big piece of this paper that was saying that we can make learn a category is to do composition properly. The problem is, so you have an A-B pair, you have your parametrized function, and you're going to update it to have new parameters. So that's what that looks like. The problem is when you start with A and C, and you're trying to compose these two learners, you're missing a B and a B prime in the middle. You're missing things in the middle to try to use your update function with. And so what you do is, well, we can use the implementation we have to generate our sort of B prime to pair with C, but you add in a request function. And this was the thing that the paper came up with. And with this request function,
This is kind of interesting, because normally I think of composition as going the opposite direction, where you're given AB and BC, and then you form AC, but here it's the opposite way. Why is that?
so you're given AB and BC, that's the I and the J here,
Oh, okay.
right? So you have I, U, and R, you have J, W, and S.
Oh, I'm going off of the
Yeah.
first sub-bullet point where you say given AC, but need AB and BC.
Right, and you get, and you're learning things about, you're doing learning now, and when you learn, you have example pairs that you're given,
Okay.
right? Inputs and outputs that you use to learn, that you train on. And the A and C come from those examples,
Okay.
okay? But in order to use what you have, which is A to B and B to C, you need to create your own examples out of the given AC example.
So there are
need
scenarios
to
where
have
you need to go in both directions then?
Hmm?
There are cases where you'll both need to compose things in a forward and backwards direction in some sense? Is that how you want to interpret this?
Not precisely. You need a. Probably should have had a nice picture for this. You need a nice way to generate examples in the middle.
2 minutes.
Before we get into this, one thing that we help me say is that every morphism here can go forward and backwards. This category is full. Every morphism in this category is one.
Okay.
So learning and forgetting.
No, doing and learning.
Okay. Oh well. Point is, we also want it to be a closed Cartesian category, which basically means that you have curry, uncurry, and apply. Right? So you have these objects which can be, so you want to be able to say that your morphisms can be functions, or your morphisms can be objects. So when you think of sets and functions, you want to be able to represent a function as a set. And one way to think about this is you can curry and uncurry your function into products. Okay? So that's the sort of intuition here. The idea is, could we write down a couple of learners and define a parameterized function between them, define a learner from that function? In other words, is it reasonable to think of, so these are two things that aren't answered in the paper and that I haven't concretely worked out in full detail, the curry and the apply. But this is sort of my intuition that curry and uncurry should work. I think it would be reasonable. I haven't written it down in detail, but I think it would be reasonable.
Do you want to wrap up?
Yeah. So basically, yeah, this will work. Then the other paper, compiling to categories, has a nifty little Haskell plugin that theoretically, if you write down some type classes for this that says these things are instances of these categories, it'll spit out learning networks for you. If the instances implements those. Theoretically, there are caveats, but that's the deal. Okay.
Thanks. Questions from Matt? Mike.
Or actually, this is the idea there. Yeah. Could you do it nicely without using something like powerful Haskell?
All right. Thank Matthew. All right. Next speaker is Mike, and we're going to clap him in.
Okay, so I'm going to be talking about region-based memory management. So first, some motivation. In case you didn't know, computers have finite memory. So it's common for a program to need to allocate more memory than you have. So we have to find some way of reusing memory after we're done with it. And ideally, we want to do this in a safe way. So we don't try to reuse memory that we don't try to dereference memory that we've already gotten rid of. But there are lots of ways we could do this. So first, let's nail down what kinds of things we care about in a way, in a strategy for handling memory management. So do we want it to be fast? Probably, although what does fast mean? Predictable. Do we want to be able to predict what the performance of our program will be? Should it be scalable? For example, should we expect it to improve in parallel speedup as we throw more cores at it? Do we want our program to be responsive? So we don't have pause times that we'll have to wait for during collection. And do we want it to be safe? Well, we probably want all of those things, but we probably can't get all of them at the same time. So the simplest example of this is just using the stack to handle memory. You've probably done this in C or languages like that, where you just say, okay, I'm going to declare these variables. They have the scope of inside this function, and that's it. When I leave this function, they're gone. So every point of allocation is paired with a deallocation point that you can look at just by looking at the code of the program. So just by looking at the C program, you can tell this array is going to be gone by the time I get to that close curly brace. So there are some flexibilities here. Like we don't necessarily need to know statically in the syntax the exact size of that array, but we do need to know how big it'll be by the point that we allocate it. So this would preclude something like a linked list. The other problem here is the lifetime of these values can't extend beyond the scope of this function. So this would make it difficult to, for example, return this array, or to do something like return a closure. So what do we do in C? Well, in C, we just say we're going to manually manage this, and it'll just be our responsibility if it doesn't work. I stole this joke from a Connor McBride paper. So in this example here, that array, we have to call malloc, because even at the point that we enter the scope, we don't know its size yet, because it's determined dynamically by calling it. So it's our responsibility to free it by the time we get to the end. So what happens if we forget to call free? Well, that memory is just gone forever. And even in this strategy, if you assume that the programmer can use malloc and free perfectly, which I can't, then the performance can still be a problem. So what about garbage collection? GC will recycle the parts of the heap that contain only unreachable values. So starting from some set of roots, for example, your stack and your registers, trace through all the values in the program, and anything that we don't get to is garbage and we can throw away. There's an oversimplification. There are lots of ways of doing garbage collection. Just bear with me. So this can be very efficient. It can even be more efficient than manual memory management because it can deallocate, for example, in bulk. A copying garbage collector doesn't have to touch the things that are garbage. They just go away. But there are still problems with it. Of course, you can still have memory leaks even with garbage collection. But what's more interesting of a problem is that we lose the sort of predictability of knowing just by looking at the program how the memory is going to be handled. We don't know necessarily when something is going to become garbage and be recycled, unlike in the stack discipline. So the proposed solution from this from the early 90s is region-based memory management. Now, in region-based memory management, it's sort of like the stack discipline, but the stack here is a stack of regions, each of which grow in unbounded size. You can see here R3 and R1 have grown large, whereas 4 and 2 are still small. These regions are introduced lexically, so they have a scope, sort of block scope, but the individual regions can continue growing even if there's a region nested inside of them. So the proposal here is that we can get most of the benefits of stack-based memory management, but apply this to the kinds of things you'd otherwise need a garbage collector for, like a higher order language with closures. So the application here originally was to do memory management for a language like ML. So in the original paper, this was paired with the idea of region inference. So you look at an ML program and you infer region annotations, which are the let regions that we saw, the let regions that will introduce these regions. So this was used in the MLKit compiler in the 90s, which is still around. Since then, people have done all sorts of things with it. You can embed a region calculus in a language like Haskell. And you can also combine it with garbage collection. So to have garbage collection happen inside these blue blocks. So the basics of this, we have these two new forms at the bottom, an expression at a region and then a let region. The let region form introduces the region in the scope of the expression, and every expression that produces a value needs to be annotated with the region. So let's look at an example here. The top is just a simple ML program that doesn't do anything useful, but it just returns, if the let expression binds x to the pair 2, 3, then we build a closure that maps y to the first of x and y, and then applies that function to 5. If we're going to annotate this with regions, we first say, okay, well, assuming regions P1, P2, and P3 are just in scope. Then we allocate 4 and 5. Then we go into it and have this let region for P6. And inside of that, we have essentially most of the body of the original program. And from this, you can see, well, the things that we need to be returned at the end, like the 5 and the 2, because those are going to be in our pair at the end, those regions have to be in scope. Whereas the rest of these things, like the 4, 5, and 6, will go out of scope. So any memory that was associated with them, like this pair here, will be collected by the end of the expression. All right, so you've seen most of the important parts of the grammar so far. One new thing here is this abstraction form, which is basically just a way of substituting in regions for a function. So a function is parameterized over the regions that it uses. And then these values I'm just writing with angle, the L angle and right angle. And they're also annotated with the region. And there's also this dot here for a dead region. We'll use this in the operational semantics to make sure that we can't use a value that lives in a dead region. So the most important rule here is the let region rule at the top at the center, where we say, well, once we've evaluated that expression to a value, what do we do? Well, because that region, the row, is going out of scope, we substitute it in for the dot inside the value. So that if anyone ever tries to use this again, it's at this dead region, and we're not allowed to dereference anything that's in a dead region. So this would simulate the fact that we've deallocated that memory. So now, from this, you would infer that a program that tries to use a value that was allocated in a region that's dead would get stuck. So if we want a language to be type safe, our type system should prevent us from being able to write a program like that. So the type system has a judgment of the form where it takes a type environment and an expression, and it gives us a type and an effect, where an effect is essentially a set of regions, which are the regions that are touched during the computation of that expression. There are also these things on the arrow and the for all stuff, which I'm going to skip because I don't have a lot of time, and effect variables, which I don't want to talk about anyway. So this is the rule that would prevent the problem we talked about earlier. So how do we know that this let region expression is well typed? Well, we have to know that this region is not contained in the free variables of either the type or the typing environment. So the reason the region can't be in the type of E is we don't want to just have the value of something that is in that region escape this scope. The more subtle thing is why the region can't be in the typing environment. That's because we could be returning a closure. And we don't want the thing returned to be able to close over the region, which would let it escape it, even if it wasn't directly typed. And once we type this, we remove the row from the effect set, because it's no longer allowed. So this is called effect masking. So this means we can type this expression as if it didn't perform an effect, because it's all internal just to this expression.
Does that mean that an effect can be viewed as a set of effect variables here?
Yes, yes. So I even put in the slide, I didn't want to talk about it, but there's a thing called an effect variable, which is the epsilon here. That's necessary because in a higher order language, you don't actually necessarily know the contents of that set. So you have to sort of leave a hole in it for when you might need to substitute that stuff in.
30 seconds.
30 seconds? Okay, well, I will go quickly. Okay, so the top row and the bottom row are the two rows for handling closures. The top one, we put the row in the effect set because we're allocating the closure. The second row, the effect set here is empty. The reason it's empty is because the thing that we're typing is a pointer to a closure. And it's just a machine value, a machine integer. We don't care about it. The row down here, you see we're building this giant effect set by unioning together all these things because this is the application rule. So we evaluate both the E1 and the E2, and all the effects are unioned together there. Really quickly, region inference, I didn't talk about it, but the intuition here is, how do we know where to put this let region? Well, a good place to put it would be a case where we know that the region row is not in the type of E or in the type expression or type environment, but it is in the effect set, which means in computing E, we used row, but row is not returned from E. So it's safe to put the let region there. Limitations, people did this in MLKit in the 90s, kind of worked out, kind of didn't. Okay, conclusion. Basically already said this stuff. So the language is designed to prevent references to data that belongs to deallocated memory. Okay?
Thanks.
Yeah.
Seems to me like in the presence of conditionals, this becomes less predictable.
Okay, well, what you're getting at would be like the two branches should be expected to have the same type, right? Okay, so I didn't show it, but there's a rule that will cut effects out of an effect set if they're not necessary. So what you actually need to say is that the type of the two conditionals, you take the sort of larger of the two effect sets.
I see.
So you don't necessarily have to perform all the effects your type says you do, but you're over approximating that. But that does lead to a problem I kind of hinted at here with how this applies to things in practice, which is if you just naively write your functional program and expect it to work like it had garbage collection, that can be a problem because you can sort of be accidentally having things like that are in a region that you don't think are in that region. So like you allocate a whole bunch of like a big list and then you return like a tiny subset of it. Well, if it lives in the same region as that whole temporary list, then you have to keep that whole thing around as long as you keep the sublist around. Yeah. So see, that kind of thing can happen accidentally in a conditional, especially if you have something like a conditional that'll return early if you fail, and you would expect it to then throw out all the stuff you were working on. Well, maybe it didn't.
So is there anyone you know of that
So there's a big extension of this, which is regions that are not lexically scoped. So that would be like an effect system where like create region and destroy region are actions. And so then you can, for example, have a conditional branches that do different things, and then you have a proof obligation at the end to prove that at some point in the program you join and they're now in the same state. So that gives you more freedom to manage when your regions are created and destroyed.
You may have said this, sorry if I missed it. The state of this, is this, you've mentioned some previous work, but it sounds like you guys are hacking on it.
Yes.
What's the current state of hacking or?
I unfortunately had to skip over the history of this a little bit. This was originally applied, in the 90s in MLKit. And they kind of came to the conclusion that it didn't work for big ML programs, and then people moved on. And since then, it's sort of been recycled in a couple of ways for doing different things. For example, like managing resource lifetimes in Haskell is a library for that. The thing that we're using it for is a little bit different than the original MLKit goal. We don't want to throw this at a gigantic existing SML program. We're designing a new language, which is designed sort of to revolve around the style of writing programs that will work well with this. And we're also extending it so the type system will allow you to talk about the actual locations of things within a region and doing a limited kind of pointer arithmetic to things that are allocated inside a single region. Which if you saw my talk on Given from last year, it's designed so that you could have something like a tree that's serialized in memory, and then have a recursive function that operates on it as if you had pointers.
So an ICFP submission?
I think a little late for that, but yeah.
So I also have to plug Eric Holt's dissertation.
Yes. That's another big one that's used this recently.
It's
Yeah.
some really cool work using regions to get functional programs onto the GPU.
Yes. And he used it in exactly the way that I think it's perfect for, which is you're in a situation you just can't use garbage collection. You need to do something that's close to C, but you still want to write functional programs. And this is exactly what you do.
If anybody wants some interesting hard research problems to play with, making that go fast.
Yeah.
How exactly do you decide which data is assigned to which region? Because the example you provided.
The code example? This one?
This one. So 2 is assigned to P2.
Yeah.
And 3 is assigned to P6.
Yeah.
And at the end, within the function, we have first x comma y is assigned to P1 and 5 is assigned to P3. So how exactly is it decided?
So this would be decided by either by a human or by region inference. The reasoning, for example, of why some things need to be at P1, P2, and P3 is because they will escape the scope of this expression. But as for why the particular values are chosen, there are various algorithms for doing region inference that will typically, the general strategy is walk through and for each thing say, okay, give me a fresh region. And then try to unify it with other things while you're going through. And if two things unify together, then they should be in the same region. You do this with constraint solving, you do this with all sorts of things. But this probably was written by a human. I took this from the Toffen paper before they had a program implemented. So I think they just sat down and wrote this. But that's the general intention. Yeah.
So with lexically scoped regions, you can imagine that there's not going to be as much function reuse as you would want. Is there any work on polymorphism of regions?
So that's part of the things I didn't talk about is you can have polymorphic recursion, for example, to have a function that will be called on different regions. So it can bind a new region and then call itself with the new region as a parameter.
Gotcha.
So this would allow you to do something like building like a tree or a graph where different parts of the structure live in different regions and have different scopes. And that's necessary. Because if you didn't do that and you tried to apply this to a big ML program, what would happen is it would say, okay, the entire program is in region P1, I'm done.
So it allows you to have cyclic data structures?
Yes.
Without losing the finer grained structure? That's okay.
You have to be very careful using cyclic structures, especially with region inference. Probably what will end up happening if you throw region inference at like a cyclic list. It'll just say the entire thing is in the same region.
All right, let's let Mike catch his breath. Thank you. Sorry about the room change. We're working on it. We tried something. We'll try something else next week. But I'd just like to thank our 3 speakers again. Thank you.
So why don't we just put a little set of